In a universe where space colonies stand as beacons of human progress, the challenge of managing waste sustainably emerges as a colossal hurdle. Within these far-flung outposts, where every resource must be preserved and repurposed, the line between thriving and surviving becomes razor-thin. How can we ensure that our celestial habitats remain clean, livable, and conducive to human life? Enter the realm of artificial intelligence and automation, offering not just solutions but a transformation in how we perceive and handle waste. In this video, we're going to delve into the innovative techniques and cutting-edge technologies that promise to revolutionize waste management in space colonies. Join us as we explore the fascinating journey of turning potential pollutants into prosperity, unveiling a future where technology and ecology intertwine on a planetary scale. Imagine for a moment the bustling life in a future space colony on Mars or perhaps the Moon. Every day brings a flurry of activity as colonists go about their daily routines, research, exploration, and building a new world. Yet, amid this exciting progress, there's a shadow growing quietly and steadily. It's the unchecked accumulation of waste, a problem that all too quickly escalates in these remote outposts where every inch of space and every resource is precious. The challenges of waste management in space colonies are as complex as they are urgent, highlighting stark differences from our practices here on Earth. Firstly, let's consider the issue of resource scarcity. On Earth, we have the comfort of virtually unlimited access to materials and the ability to transport waste away from sight and thought. In stark contrast, space colonies operate within a closed-loop system, meaning that every resource once shipped from Earth must be conserved and repurposed to the greatest extent possible. There are no nearby landfills to dump garbage into, no vast oceans to dilute our refuse. The space available is limited, and the cost of sending new materials from Earth is prohibitively high. This scarcity turns waste into a potential asset if we can process and repurpose it effectively. In addition, the harsh environments on Mars and the Moon pose unique hurdles. For example, the varying gravity fields affect how we might manage waste. A low-gravity environment impacts the movements of both people and materials, influencing how waste is collected, transported, and processed. Moreover, temperatures can swing from scorching to freezing, adding another layer of complexity to waste handling technologies, which must be robust and adaptable to such conditions. The ecological impact of waste on these pristine extraterrestrial bodies is another critical concern. While space itself seems boundless, space colonies must tread carefully to avoid disrupting delicate new ecosystems that might eventually develop. The accumulation of waste not only poses a risk to these potential ecosystems, but also to human health. Waste-related pathogens and hazardous materials could easily compromise the air and water supply within a colony's limited environment, making space waste management not just a logistical issue but a public health imperative. Expert insights into these issues reveal that traditional Earth-based waste systems are ill-equipped to handle the unique demands of a space colony. For instance, our reliance on massive infrastructure for waste collection and disposal simply does not translate to a small and self-contained environment. Furthermore, the sheer energy requirements needed to manage waste using current Earth technology would be unsustainable in space. This gap signals the urgent need for novel approaches. The development and integration of innovative technologies such as smart waste sorting, in situ resource utilization, and material recycling could be the game changers that turn waste from a problem into a resource. Understanding this complexity underscores why new technological interventions are not just beneficial but essential. They're poised to redefine how we approach waste in these new frontiers, promising a future where waste becomes a managed, minimized component of life rather than a mounting obstacle. As we move forward, these innovative strategies will not only safeguard the health of future colonists, but also preserve the nascent ecosystems on Mars and the Moon, ensuring that our extraterrestrial neighbors remain as pristine and life-sustaining as we hope to find them. Imagine stepping into a futuristic waste management facility on a distant Martian colony, where AI-driven robots diligently sort through trash with an accuracy that far surpasses human capabilities. These intelligent machines don't just sift through waste, they transform the entire process into a symphony of efficiency and precision. Using advanced algorithms, these robots employ machine learning to continually enhance the way waste is categorized and separated, learning and adapting with every piece of material they process. On Earth, we've already seen glimpses of how artificial intelligence can revolutionize waste management. Take, for example, the AI systems deployed in advanced recycling facilities. These systems use computer vision to identify and sort various types of materials, from plastics and metals to organic waste. They execute this with precision and speed, turning what would be a labor-intensive task for humans into a streamlined process that maximizes recycling rates and minimizes contamination. But how do these Earth-based innovations translate to the unique challenges of space? In a space colony, the stakes are much higher. The confines of a closed-loop system mean that optimal resource recovery isn't just preferable, it's essential for the colony's survival. Space waste sorting robots are thus equipped with enhanced sensory and processing capabilities tailored to extraterrestrial environments. They utilize multispectral imaging to analyze waste composition in ways that are immune to the low-light conditions of space habitats. Additionally, their lightweight, durable designs allow them to function efficiently within the constraints of reduced gravity. The AI algorithms in space waste management go beyond simple sorting. They embody a learning system, constantly analyzing data to improve accuracy and efficiency. For example, as a robot classifies waste items, it gathers data about materials it encounters most frequently, adjusting its sorting patterns to maximize resource recovery. This adaptability not only reduces human error, but also ensures that valuable resources are not inadvertently discarded, which could be detrimental in a setting where every ounce of material counts. Experts highlight that the integration of AI into waste sorting processes leads to a significant increase in the efficiency and effectiveness of recycling efforts, particularly in environments where human oversight is limited or impractical. By minimizing human involvement, these AI systems reduce errors and enhance safety, freeing human resources for other critical tasks within the colony. Moreover, the evolving role of AI in waste management is shaping the future of space sustainability by fostering a circular economy within these colonies. Materials once destined for disposal are now being reclaimed and reintegrated into the colony's supply chain, creating a sustainable cycle of use and reuse. This not only conserves precious resources but also minimizes the ecological footprint of human habitation on other planets. As AI continues to develop, its role in waste management could become even more sophisticated, potentially predicting waste generation trends and preemptively managing resources with an efficiency born from millions of data points processed in real time. The implications of this technology extend beyond practical waste management, inspiring a new ethos for how we approach sustainability on Earth and beyond. By investing in these automated systems powered by AI, future space colonies can set a precedent for zero-waste living, demonstrating that with the right technologies, human expansion across the stars can be achieved without compromising the health of distant worlds. As these robotic custodians of cleanliness and conservation continue to evolve, they bring with them the promise of a sustainable future, one where waste is no longer an insurmountable challenge but an opportunity to thrive sustainably among the stars. Now, let's envision a world where waste is not just managed but transformed into a treasure trove of vital resources, all thanks to the magic of automation. In the unique realm of zero-gravity space colonies, automated systems work around the clock, seamlessly converting space waste into valuable commodities. Imagine robotic incinerators, 3D printers using recycled materials, and other cutting-edge technologies all collaborating to reimagine how waste is processed and utilized. At the heart of this transformation are robotic incinerators, acting as the frontline soldiers in the war against waste. These sophisticated machines are engineered to operate without human intervention, burning organic and certain inorganic waste materials at controlled high temperatures to produce energy, a commodity as precious as gold in the isolated environment of a space colony. The energy harnessed from this process can power colony operations, reduce the need for transported fuel, and significantly cut down the colony's carbon footprint. Automated control systems manage these incinerators with precision, ensuring optimal combustion conditions while reducing emissions and converting byproducts into usable forms, such as ash for soil enhancement in agricultural zones. But the innovation doesn't stop at incineration. 3D printing technology is taking recycling to a whole new level. Picture advanced 3D printers that don't rely on new raw materials. Instead, they utilize plastics and metals salvaged from waste, reimagining our concept of trash. These printers can produce a myriad of essential items, from repair parts to tools and even building components. This technology not only maximizes resource efficiency, but also minimizes logistics costs. There's no need for regular resupply missions from Earth. With automation at the helm, the dependency on human labor drastically decreases. Colonists are no longer tied down by labor-intensive waste management duties. Instead, they can focus on the scientific exploration and development that space colonies are intended for. This shift in labor dynamics is crucial. It allows for a reallocation of human resources towards innovation, research, and the creation of new technologies that further advance the sustainability and viability of life beyond Earth. Real-world applications of automated waste processing are already paving the way for these space-age advancements. For instance, Earth-based facilities are trialing robotic waste sorters and incinerators that require minimal human oversight, robots that sift and segregate materials with unmatched accuracy. The integration of similar technologies into space ecosystems is poised to revolutionize how we approach waste management, making it not just a process of disposal but one of resource reclamation and reuse. Moreover, automation technology offers the potential to construct entirely autonomous waste processing units. These units, strategically placed in a space colony, could independently handle all aspects of waste management, from collection through to processing and recycling. Such advancements would not only enhance the self-sufficiency of space colonies, but also ensure that waste is consistently turned into valuable resources without the need for continuous human input or intervention. The roadmap to fully automated waste management systems in space colonies is laden with promise and potential. As these technologies evolve, they will transform how waste is perceived, turning it from a challenge into an opportunity. In embracing these innovations, we set the stage for a sustainable future in space, where human ingenuity and technological prowess join forces to create a truly circular economy. It is a vision where waste is no longer a burden but a stepping stone to building thriving human habitats among the stars. Picture a network of advanced sensors and AI working harmoniously in the dynamic environment of a space colony. This is the future of smart waste collection systems, where technology not only manages waste but does so with an intelligence and efficiency that ensures the sustainability of these cosmic communities. In the vast corridors of space habitats, every waste bin, disposal unit, and processing center is interconnected through an intricate web of Internet of Things devices. These devices work together to monitor waste levels, predict collection needs, and orchestrate the most efficient collection and disposal pathways. The integration of the Internet of Things with AI stands at the forefront of this revolution. Intelligent sensors fitted to waste receptacles communicate wirelessly, transmitting real-time data on fill levels, waste types, and locations. This data is processed by AI systems that analyze patterns and predict peak waste generation times. The result is an optimized schedule for waste collection, ensuring it occurs just in time, neither so late that bins overflow nor so early that resources are wasted on unnecessary trips. Imagine autonomous vehicles specially designed to navigate the unique challenges of microgravity, seamlessly maneuvering through space habitats. These vehicles, equipped with robotic arms and precision navigation systems, are responsible for waste collection and transport. They follow the AI-generated routes, which are dynamically adjusted in response to real-time data, ensuring that waste is collected at the most efficient times and transported to processing units with minimal energy consumption. These vehicles are a marvel of engineering, designed to move with agility and precision, handling waste containers as easily as if they were feathers, thanks to microgravity conditions. On Earth, we've already seen the successful implementation of smart waste management systems serving as a model for what might be achieved in space. Cities like Barcelona and Seoul have implemented sensor-equipped bins that alert collection services when they need to be emptied. These systems have proven to drastically reduce the number of unnecessary collection trips, cutting fuel use and lowering emissions while keeping the streets cleaner. This kind of efficiency and adaptability is precisely what space colonies require, albeit with tailored solutions to meet the unique challenges of space environments. Furthermore, these smart systems aim to minimize energy consumption, a critical factor in the energy-conscious world of space colonies. Waste collection must be meticulously managed to conserve the limited energy resources available. With AI optimizing routes and schedules, autonomous vehicles can operate in a way that maximizes efficiency and reduces the colony's overall energy footprint. This is particularly vital in space, where every watt of energy saved can be redirected to other essential operations, from life support to scientific research. The benefits of such smart waste systems extend beyond energy savings. They contribute to the overall sustainability and livability of space habitats by ensuring that waste is efficiently managed and resources are conserved. This proactive approach reduces the risk of waste becoming a health hazard or a source of contamination, ensuring that space colonies remain clean and safe environments for their inhabitants. In conclusion, the vision of smart waste collection systems powered by EOT and AI represents a significant leap forward in how we manage resources in space. By drawing inspiration from successful Earth-based models and adapting them for extraterrestrial use, we can create intelligent systems that not only meet the needs of space colonies but also set a new standard for sustainable living. These innovations ensure that as we extend our reach into the cosmos, we do so responsibly, preserving the delicate balance of these new frontiers. Imagine the prospect of waste, a once burdensome byproduct of daily life, being turned into a powerful source of renewable energy to fuel entire space colonies. In the realm of space settlements, where resources are precious and scarce, the transformation of waste into energy is not just revolutionary but essential. Technologies like anaerobic digestion and pyrolysis are paving the way for this energy revolution, turning what was once considered refuse into a crucial component of survival and sustainability in space. Anaerobic digestion is a biological process where organic waste is broken down by bacteria in the absence of oxygen, producing biogas, a mixture of methane and carbon dioxide. On Earth, this process is already utilized to convert agricultural and municipal waste into a renewable energy source. In the closed-loop systems of space colonies, anaerobic digestion can be particularly valuable. It not only reduces the volume of waste but also generates biogas that can be harnessed to produce heat and electricity, essential for powering life support systems and other vital infrastructure within the colony. Pyrolysis, on the other hand, involves the thermal decomposition of materials at high temperatures in an inert atmosphere. This process transforms solid waste into syngas, bio-oil, and biochar. Syngas, primarily composed of hydrogen and carbon monoxide, can be used to generate electricity or serve as a precursor for producing fuels and chemicals. Biochar can be applied as a soil amendment, improving soil fertility, a vital component for any space-based agricultural endeavor. Adapting these technologies for space presents several challenges. The reduced gravity environment affects the handling and processing of both input materials and end products. Moreover, the setup and maintenance of such systems require robust and reliable technology capable of functioning with minimal human intervention. Waste processing facilities must be compact and efficient, given the limited space available in a colony. Engineers and scientists are constantly innovating, developing miniaturized and highly efficient digestion and pyrolysis units that can operate autonomously, adjusting to the unique conditions of space habitation. Despite these challenges, breakthroughs are continually being made. For instance, researchers are exploring the use of genetically engineered bacteria to enhance the efficiency of anaerobic digestion under varying temperatures and pressures found in space. Similarly, advanced materials and designs are being tested to optimize pyrolysis units, enabling them to handle a diverse range of materials with minimal energy input, a critical consideration when energy conservation is paramount. Experts underscore the importance of maximizing energy recovery from waste as a cornerstone of sustainable living on other planets. Dr. Sarah Lawson, a leading researcher in space sustainable systems, notes, "Harnessing energy from waste not only alleviates the burden of waste management, but also provides a renewable energy source that is crucial for the self-sufficiency of space colonies." It's about creating a closed-loop system where every piece of waste is seen as a potential resource. Energy recovery from waste offsets waste production and contributes to the creation of self-sufficient colonies. By turning waste into a valuable energy source, colonies can reduce their dependency on Earth for resupply missions, lowering the cost and environmental impact associated with launching materials from our planet. This approach also supports the development of a circular economy in space, where materials are continually reused and recycled, ensuring the long-term viability and sustainability of human life beyond Earth. In this pursuit, the vision of waste-to-energy technologies becomes a beacon of hope, guiding us toward a future where space colonies are not only feasible but thriving ecosystems of innovation and sustainability. As we continue to push the boundaries of exploration, embracing these technologies will ensure that our interstellar endeavors are as sustainable as they are ambitious. Through the lens of waste to energy, we learn that in the vast expanse of space, nothing is truly wasted. Instead, every discarded item can be the spark that powers our journey to the stars. Imagine the scene. In the heart of a bustling space colony, autonomous robots glide effortlessly through narrow corridors and expansive modules, executing their waste management duties with precision and reliability far beyond human capability. These robots are not just tools but integral components of the colony's infrastructure, ensuring that waste is handled efficiently and safely in the extreme and unforgiving environment of space. The role of robotics in automating waste management processes begins with collection. Equipped with advanced sensors and machine learning algorithms, these robots can assess waste levels in various receptacles across the colony. When bins reach capacity, these robotic units autonomously navigate from their docking stations, using LiDAR and infrared sensors to avoid obstacles and ensure safe passage through the colony's network of compartments. Their movements are coordinated via a centralized system that optimizes paths to minimize energy consumption and time, reflecting an efficiency that is critical when every resource in space is at a premium. Sorting comes next, a process where robotics truly shines. In an environment where humans may struggle with even simple tasks due to bulky spacesuits or microgravity, robots are unfazed. They utilize sophisticated vision systems powered by artificial intelligence to identify and categorize materials at astonishing speeds. Whether it's distinguishing between different types of plastics and metals or identifying organic waste for recycling, these robots process waste with an accuracy that ensures maximum resource recovery and minimizes contamination. This capability not only reduces the volume of waste that must be managed but also enhances recycling efforts, turning potential waste into valuable resources that can be reused or repurposed. Processing waste in the unique conditions of a space colony presents challenges that robotics is well suited to overcome. For tasks that involve exposure to hazardous materials or extreme conditions, robots take on roles that would be unsafe for human workers. They manage incineration processes, control anaerobic digesters, or operate pyrolysis units, all while withstanding temperatures and handling materials that would pose significant risks to human health. By delegating these potentially dangerous tasks to machines, colonies ensure the safety of their human inhabitants while maintaining continuous and effective waste management operations. The advancements in robotic technology enabling these capabilities are nothing short of remarkable. Modern robots are built with lightweight yet durable materials, making them ideal for the rigors of space. They feature modular designs, allowing for easy repairs and upgrades, which is crucial in an environment where spare parts and human intervention are limited. These robots are also equipped with self-diagnostic tools, enabling them to detect and resolve issues autonomously, further reducing the need for human oversight and ensuring uninterrupted operation. Beyond efficiency, robotics plays a pivotal role in enhancing the sustainability of space habitats. By automating and optimizing waste management processes, robots help maintain environmental balance within the closed systems of a colony. They ensure that waste doesn't accumulate to levels that could threaten the health or operational viability of the colony. They also contribute to the creation of a closed-loop system where materials are continuously repurposed, supporting the colony's self-sufficiency and reducing reliance on resupply missions from Earth. In conclusion, robotics in waste management is not merely a convenience but a necessity for space colonies striving to be sustainable and autonomous. These technologies transform how waste is handled, turning a potential challenge into an opportunity for resource conservation and innovation. As we look to the future, the integration of robotics in space waste management will undoubtedly evolve, pushing the boundaries of what is possible and ensuring that as humanity reaches for the stars, it does so responsibly and sustainably. Imagine a future where space colonies operate within a meticulous closed-loop system, a cycle so efficient that every discarded item finds new life as a valuable resource. This isn't just a dream, it's a necessity for humanity's survival in the vast expanse of space. To make this vision a reality, innovative recycling technologies must evolve, tailored to the unique challenges of space habitation. Among these, chemical recycling and bioconversion stand at the forefront, promising to transform waste management in space colonies from a looming threat into an asset of sustainability. Chemical recycling involves breaking down plastics and other materials into their fundamental building blocks through chemical processes. Unlike traditional recycling, which often degrades material quality, chemical recycling allows for the creation of new, high-quality products. In the confines of a space colony, this technology serves as a crucial component of resource recovery. Imagine a system where plastic waste is not just shredded but converted into raw materials like monomers or polymers that can be reused in manufacturing processes. This capability enables colonies to regenerate essential components, minimizing dependency on Earth-based resources and reducing the environmental footprint of continual resupply missions. Bioconversion, on the other hand, leverages biological processes to convert organic waste into useful products. This method utilizes microorganisms to transform waste into biogas, biofuels, or even organic fertilizers. In space, where maintaining a sustainable agricultural system is vital, bioconversion can provide nutrients to support plant growth, closing the loop between waste generation and food production. This method not only ensures that organic waste is effectively managed, but also supports the creation of a self-sufficient ecosystem within the colony. But how do these advanced recycling technologies reach their full potential in space? The answer lies in the integration of artificial intelligence. AI plays a critical role in optimizing resource recovery processes, using machine learning algorithms to identify and sort waste with pinpoint accuracy. By continuously analyzing waste composition data, AI systems can adapt recycling processes in real time, ensuring that every piece of waste is processed most efficiently and effectively. This dynamic optimization is key to achieving a near-zero waste status, where almost nothing is discarded and everything is repurposed. On Earth, we've already seen the transformative impact of AI-enhanced recycling systems. Consider the case of recycling facilities in urban centers like San Francisco and Tokyo, where AI-driven machines have replaced traditional sorting methods. These systems utilize computer vision to distinguish between different materials, sorting them with a level of precision that significantly reduces contamination rates. The experiences from these Earth-based systems provide invaluable insights for space applications, illustrating how advanced technologies can elevate recycling efficiency and sustainability. As we look to the potential of space colonies to achieve near-zero waste, these technologies offer a promising blueprint. By repurposing waste in innovative ways, space colonies can reduce their environmental impact and enhance their sustainability. For example, using chemical recycling and bioconversion in tandem can turn a broad spectrum of waste types into vital resources, supporting everything from infrastructure repair to agricultural viability. This holistic approach not only preserves the pristine nature of extraterrestrial environments, but also fosters a culture of sustainability that can be mirrored back on Earth. Ultimately, the pursuit of near-zero waste in space colonies isn't just about survival, it's about setting a pioneering example of how humanity can live harmoniously within our planet's limits. The lessons learned and technologies developed in these extraterrestrial endeavors could redefine waste management practices on Earth, promoting a global shift towards more sustainable and circular economies. In this light, space colonies are not just a new frontier for exploration. They are a catalyst for innovation, pushing us towards a future where waste is viewed not as a problem but as an opportunity for transformation and growth. Picture this: the frontier of space exploration is not just about discovering new worlds, but about mastering the art of sustainable living in some of the harshest environments imaginable. As we reach further into the cosmos with ambitions of building sustainable colonies, one of the most formidable challenges we face is waste management. The reality of handling waste in space colonies presents a unique set of obstacles. At the forefront of these are the technical limitations inherent in deploying AI and automation technologies, along with concerns about cost and ethics. Let's start with the technical challenges. Space environments strain the capabilities of current technologies. For instance, AI systems that work seamlessly on Earth under controlled conditions might struggle with the unpredictability of space. The effects of cosmic radiation and the microgravity environment can degrade electronic components and disrupt the functionality of automated systems. Designing machines that can withstand such conditions requires advancements in materials science and engineering, adding layers of complexity to AI implementation in space colonies. Then there's the matter of cost. The development and deployment of sophisticated AI and automation technology come with a hefty price tag. The investment required for research, testing, and scaling these technologies can be prohibitive. This is particularly relevant when considering the budget constraints of space exploration missions. The initial cost of deploying robotic waste management systems in a space colony might seem daunting, but the long-term savings in resource conservation and reduced resupply needs could outweigh the upfront expenditure. Ethical considerations add another dimension to the challenge. The use of AI and automation in waste management raises questions about the transparency and accountability of these systems. For example, programming AI to make decisions about resource allocation could potentially lead to biases or errors that compromise safety or sustainability. There is also the issue of data privacy and how much oversight and control colonists should have over these automated systems. However, these challenges have not gone unaddressed. Ongoing research and technological advancements are paving the way for more effective solutions. Scientists and engineers are pushing the boundaries of what's possible, developing AI systems that learn and adapt to the unique conditions of space. For instance, machine learning algorithms are being trained to improve their decision-making under variable conditions, ensuring that waste is managed efficiently even when faced with unexpected challenges. In terms of technical innovations, self-repairing materials and components are being developed. These materials can detect small damages and repair themselves, significantly extending the lifespan of robots operating in space's harsh conditions. Furthermore, the use of modular robotics allows for parts to be easily replaced or upgraded, ensuring that the entire system doesn't become obsolete when a single component fails. Balancing technological progress with ecological preservation is crucial. The aim is not to dominate space environments with technology, but to integrate smoothly into the existing ecosystems, ensuring minimal disruption. This involves using biomimetic designs, drawing inspiration from natural systems to create technologies that function in harmony with the environment. For example, waste processing units could mimic natural decomposition processes, breaking down organic matter efficiently without harmful byproducts. The drive to overcome the challenges of space waste management is a testament to human ingenuity and resilience. As we seek to establish sustainable space colonies, these innovations offer a path forward, promising to revolutionize how we handle waste beyond Earth. This constant quest for improvement and adaptation ensures that as we look to the stars, we do so with a commitment to both technological excellence and the preservation of the cosmic environments we encounter. As we navigate the promising yet challenging path of waste management in space colonies, let's draw inspiration from several pioneering case studies that highlight the transformative power of AI and automation. These real-world examples offer a glimpse into how innovative waste management solutions can lead to breakthroughs in sustainability and efficiency, providing valuable lessons for future extraterrestrial colonies. One notable example is the European Space Agency's MILI-SSA project, short for Micro-Ecological Life Support System Alternative. This initiative, originally designed for long-term human missions in space, focuses on closed-loop life support systems where waste is recycled to create essential resources like food, water, and oxygen. MILI-SSA employs a combination of biological and technological processes to break down waste products into nutrients. AI plays a pivotal role by monitoring and optimizing these processes, ensuring the balance needed for a sustainable ecosystem. The project demonstrates how integrating recycling into life support systems can not only sustain life but enhance self-sufficiency in isolated environments, a crucial step for space colonies. Another groundbreaking project is NASA ISS Waste Management System, which serves as a testbed for future space missions. The system uses automation and AI to manage waste onboard the International Space Station. By automating the sorting and compacting of waste, the system reduces the need for additional storage space and lowers the dependency on resupply missions. This has direct implications for sustainability, as less frequent resupply missions reduce the carbon footprint of space travel. The ISS's waste management strategies are continually evolving, offering a scalable model for handling waste in larger space colonies. Furthermore, in a simulated environment closer to Earth, the advanced closed-loop system at the Johnson Space Center showcases how waste can be transformed into useful resources. This system employs advanced robotics to categorize and process waste, turning it into fuel, water, or raw materials. One key takeaway from this project is the importance of modularity. Its design allows for components to be easily updated or replaced, a necessity in space where maintenance opportunities are rare. The success of this simulation underscores the potential for scalable waste management systems that can adapt to the needs of different space habitats. These case studies not only reveal innovative approaches to waste management, but also highlight the vital role of AI and automation in achieving sustainability. They teach us that smart design, coupled with technology, can minimize waste and maximize resource recovery, lessons that are just as applicable on Earth as they are in space. The implications for Earth-based initiatives are profound. Urban centers around the world can draw parallels with these space endeavors, adopting similar AI-driven systems to enhance their waste management strategies. Cities like Amsterdam and Tokyo are already implementing automated waste sorting and smart bins, inspired in part by these initiatives. This interconnection between space and Earth innovations reflects a growing understanding that sustainable practices developed for space can be mirrored in urban environments, fostering a global shift towards more efficient and environmentally friendly waste management systems. As we look to the future, the successes and insights gained from these pioneering efforts will guide the development of waste management systems that support thriving, sustainable space colonies. By embracing these technologies, we not only advance our capabilities in space exploration, but also pave the way for more sustainable practices here on Earth. These efforts remind us that the challenges of managing waste aren't just about disposal, but about reimagining waste as an integral part of a sustainable life cycle, an idea that is as inspiring as it is essential. As we look toward the horizon of space exploration, the future trends in space waste management present a fascinating tapestry of innovation driven by AI and automation. As the foundation of future space colonization, these trends are poised to tackle one of the most pressing challenges: managing waste efficiently and sustainably in extraterrestrial environments. Let's explore some of the emerging trends that are set to redefine waste management in space and how they pave the way for sustainable living beyond Earth. One of the most promising developments is AI-driven predictive maintenance. This involves using machine learning algorithms to predict when waste management systems will require maintenance, effectively preempting failures before they occur. In space, where mechanical failures can have dire consequences, predictive maintenance provides a safety net, ensuring that waste processing units remain operational without unexpected downtimes. By analyzing data from sensors embedded in waste management machinery, these algorithms can detect patterns and anomalies that indicate potential breakdowns. This proactive approach not only enhances the reliability of these systems but also optimizes their performance, reducing operational costs and extending their lifespan, a critical consideration in resource-limited space colonies. Another burgeoning trend is the development of fully autonomous waste management systems. These systems are designed to operate with little to no human intervention, utilizing AI and robotics to handle every aspect of waste processing autonomously. From collection and sorting to recycling and disposal, autonomous systems can streamline operations, allowing human colonists to focus on other essential activities, such as research and resource cultivation. The use of autonomy is crucial in space environments where human labor is limited and often occupied with mission-critical tasks. These systems are designed to adapt to changing conditions and varying waste streams, ensuring flexible and efficient waste management that can evolve with the colony's needs. International collaboration represents a significant pillar of progress in the field of space waste management. As countries around the world engage in space exploration, the pooling of resources and technology accelerates innovation and reduces duplication of efforts. Collaborations among spacefaring nations and international organizations facilitate the sharing of data, research findings, and best practices. This cooperation not only expedites technological advancements, but also ensures that waste management solutions are universally robust and applicable across different environments. Initiatives like the International Space Station have already demonstrated the power of such collaboration, setting a precedent for future partnerships that transcend borders in pursuit of sustainable space exploration. Expert insights into these emerging trends highlight a long-term vision for sustainable waste practices in extraterrestrial settings, according to Dr. Emily Chen, a leading expert in space systems engineering. The future of space waste management lies in our ability to predict, adapt, and automate. By integrating AI deeply into waste systems, we create resilient frameworks that mirror Earth's natural ecosystems, efficient, adaptable, and sustainable. This vision underscores the goal of creating closed-loop systems where waste is continuously repurposed, supporting a self-sustaining habitat where resources are conserved and environmental impact is minimized. As we anticipate these technological advancements, viewers are encouraged to imagine a future where space colonies not only thrive but set an example for sustainability that echoes back to Earth. As AI and automation in waste management continue to evolve, they hold the promise of transforming space colonies into models of sustainable living, where every piece of waste finds its purpose and contributes to the thriving ecosystem of human life in space. Through this lens, the journey towards advanced waste management technologies in space is not just about solving practical challenges. It is an inspiring testament to human ingenuity and the endless possibilities that arise when we blend technology with a commitment to sustainability. As we continue to push the boundaries of our reach into the cosmos, these advancements will ensure that our footprints in space are as minimal and sustainable as our dreams are expansive. As we conclude this exploration into the transformative power of AI and automation in revolutionizing waste management for space colonies, it becomes clear that these technologies are not just solving isolated problems, but are redefining how we envision sustainability in the final frontier. Throughout this video, we have delved into cutting-edge technologies and innovative approaches that promise to turn the daunting challenge of waste management into an opportunity for sustainable living in space. We've seen how AI-driven systems, with their predictive maintenance and autonomous capabilities, are poised to handle waste with unprecedented efficiency and precision. By anticipating needs and autonomously managing waste cycles, these systems ensure that space colonies remain self-sufficient, reducing the need for frequent supply missions from Earth. This not only conserves resources but also lays the groundwork for a sustainable presence among the stars. We've also explored the remarkable potential of converting waste into energy. Technologies like anaerobic digestion and pyrolysis offer solutions that transform organic and inorganic waste into valuable resources, powering colonies and supporting agricultural initiatives. This circular approach ensures that every piece of waste contributes to the colony's survival, echoing principles of sustainability that can and should be mirrored on Earth. Reflecting on these insights, it's evident that sustainable waste practices are pivotal not just for colonizing other planets, but also hold lessons for tackling Earth's waste challenges. The innovations and efficiency achieved in space can inspire Earth-bound waste management systems, pushing us toward smarter, more sustainable solutions that benefit our planet. As we stand on the cusp of a new era in space exploration, these advancements invite us to consider the broader implications of our actions. What might we achieve if the same ingenuity and commitment to sustainability applied in space were harnessed across the globe? The potential is boundless, and it starts with taking responsibility for how we handle waste wherever we are. With a sense of optimism and curiosity about the future of human life beyond Earth, I invite you to engage with this content. Share your thoughts on how these technologies might transform our world, both above and below the clouds. Consider subscribing to stay tuned for more discussions on future-oriented topics that push the boundaries of what we know and challenge us to think differently. In closing, as we dream of new worlds, let us not forget the lessons learned here on our own. The story of sustainable space exploration reminds us that every step toward the stars is a step toward understanding our place in the universe. It's a journey of innovation, responsibility, and hope, one where waste is no longer an end but a beginning. Thank you for joining this exploration. Until next time, keep looking up and let your curiosity guide you to new horizons.